Okay, let's dive into this. Welcome back to The Explainer. Today, we're taking a trip to the absolute extremes of our universe. We're going to look at what gets left behind when the most massive stars out there finally run out of gas. And we're not talking about stars that just, quietly fade away into the night. We are getting right into the intense, mind-bending physics of neutron stars and pulsars. To really get why these objects completely break our understanding of physics, you've got to wrap your head around their density. Just imagine taking the entire mass of our sun, which is a star over 1,000,000 times larger than Earth, and somehow crushing the whole thing down into a sphere the size of a city. Because of that insane compression, just a single teaspoon of neutron star stuff would weigh billions of tons here on Earth. I mean, billions! Part 1. The violent star death. To figure out how something this wild even comes to be, we have to look at how these massive stars actually die. Let's move to and see how this builds across the whole stellar life cycle. We're talking specifically about the big ones, stars packing about 8 to 25 times the mass of our own sun. They start off in the main sequence, happily fusing hydrogen in their cores. Then, as they get older, they swell up into red supergiants, fusing heavier and heavier elements. But eventually, the fuel runs out. And when it does, without that outward push of nuclear fusion, gravity takes over instantly. You get a catastrophic core collapse, a massive supernova explosion, and what's left over is the remnant. Right during that core collapse, the microscopic physics are just pushed to the absolute breaking point. The gravity is so immensely strong that all the empty space inside an atom, it's completely erased. It literally crushes protons and electrons together in a process we call neutronization. They fuse to form neutrons and shoot off these tiny, elusive particles called neutrinos. So when the supernova finally clears, what you're left with is this incredibly hot, dense ball made almost entirely of neutrons. Part 2. Inside a neutron star. So now that we know how they're born, let's zoom in a bit and look at the actual anatomy of this remnant. We talked about density a second ago, but looking at the actual numbers really drives it home. 10 to the 17th kilograms per cubic meter. At that level, matter completely defies anything we can comprehend on Earth. It is basically just one giant atomic nucleus stretching maybe 10 to 15 kilometers across. And because you have so much mass shoved into such a tiny space, the surface gravity hits an unbelievable 10 to the 11. To put that in perspective, the gravitational pull you'd feel standing on the surface is 100 billion times stronger than what you're feeling right now sitting on Earth. Oh, and the surface is roasting at around 1,000,000 degrees Kelvin. So, absolutely do not forget your sunscreen. What's really fascinating here is how the physical state of the matter just keeps getting stranger the deeper down you go. Up at the outer crust, you've got a rigid layer of dense atomic nuclei swimming in a sea of electrons. But travel a bit deeper into the inner crust, and the pressure is so intense that neutrons literally begin to drip right out of the nuclei. Finally, if you make it to the core, you hit a frictionless liquid, superfluid neutrons, and potentially forms of matter even weirder than that. Now, you might be wondering, with gravity that intense, why doesn't the whole thing just keep collapsing until it forms a black hole? Well, the answer is quantum mechanics. There's this invisible outward force fighting against that crushing gravity, known as neutron degeneracy pressure. It's driven by the Pauli exclusion principle. You can think of it like this microscopic high-stakes game of musical chairs where no two neutrons are allowed to sit in the exact same seat. It's this incredibly stubborn quantum rule that physically props up the entire star. And alongside that massive gravity, you also get massive magnetism. For comparison, Earth's magnetic field, the one that protects our atmosphere and makes our compasses work, is a very gentle 50 microtesla. But a standard neutron star, it rocks a magnetic field between 10 to the 8th and 10 to the 11th Tesla. There's actually a special ultramagnetic class of these things called magnetars. Their magnetic fields are so outrageously strong, they can physically stretch out the shape of atoms, and they blast these intense bursts of gamma rays all the way across the galaxy. Part 3. Pulsars, cosmic lighthouses. So, what happens when you take an object this dense and this magnetic and make it spin rapidly? Well, it becomes incredibly dynamic. And that brings us to the pulsar, which is basically a rapidly rotating neutron star. Because of the conservation of angular momentum, when the massive original star collapsed and shrank into that tiny sphere, its spin sped up dramatically. Think of that classic visual of an ice skater spinning around, right? When they pull their arms in close to their body, they spin way faster. Pulsars do the exact same thing, with rotation periods ranging from a few seconds down to literally milliseconds. And this brilliantly illustrates what we call the lighthouse model. Because of that crazy spin, the intensely strong magnetic poles funnel beams of electromagnetic radiation straight out into space. As the star rotates, those beams sweep across the cosmos. If, and only if, one of those beams happens to sweep right across Earth's line of sight, our telescopes pick it up as a sharp, regular pulse of energy. It's exactly like standing in the dark and watching a lighthouse beam sweep across the ocean. But not all pulsars are exactly the same. We usually categorize them by the kind of energy they emit and just how fast they're spinning. Radio pulsars are the most common ones we spot. Then you have X-ray pulsars, which are mostly found in binary systems, where they're stealing matter from a partner star, crashing it onto their surface, and blasting out high-energy X-rays. And then we have the absolute speed demons, millisecond pulsars. These things can spin up to 700 times every single second. Their timing is so flawlessly perfect that they rival and sometimes even beat the accuracy of our best atomic clocks. But here's the catch. Despite having that incredible atomic clock-level precision, they aren't completely immune to a few hiccups. Every once in a while, a pulsar will experience what we call a glitch. It's this sudden, totally unpredictable tiny jump in its spinning speed. Astrophysicists think these glitches are caused by literal cosmic star quakes happening in the crust or down in that superfluid core, which causes a momentary, rapid shift in momentum. Part 4, collisions and the bigger picture. Let's pull the camera back for a second. How do these extreme remnants actually interact with their neighborhoods and the rest of the universe? Well, a lot of the time, neutron stars are locked in this fatal cosmic dance with a companion star. The neutron star's gravity is so immense, it acts like a giant vacuum, literally stripping matter right off its partner. As all that stolen material crashes down onto the surface, it releases enormous amounts of X-ray energy. And all that incoming matter acts like an engine, basically spinning up the neutron star until it hits those insane millisecond speeds. So the crucial point is that these remnants aren't just some weird, isolated oddities. They are deeply, deeply connected to the very makeup of our universe. Back in 2017, the LIGO Observatory actually detected gravitational waves coming from two neutron stars violently smashing into each other. And that observation confirms something absolutely amazing. These collisions are literal cosmic factories. The extreme forces of that merger create heavy elements that normal star fusion just can't make. So the gold in your jewelry? Yeah, it was very likely forged in the violent collision of two neutron stars. How cool is that? Now, when you're talking about cosmic extremes on this scale, you're probably wondering how neutron stars stack up against black holes. While they're both born from massive star death, there are some pretty big differences. A neutron star actually still has a tangible, physical surface that you could theoretically hit. And while it would be incredibly hard, escaping its gravity is technically possible. It's got a radius of about 10 kilometers, and we know it's mostly compressed neutrons. A black hole, though? No physical surface at all. Just an event horizon where nothing, not even light, can escape. And what exactly makes up the singularity inside? That is still a complete mystery to modern physics. Part 5. Why these remnants matter. As we start to wrap up this explainer, we really have to ask, why does studying all this matter so much to science? Basically, neutron stars and pulsars are the universe's ultimate natural laboratories. Because their spinning pulses are so perfectly regular, they act like highly precise cosmic clocks scattered all over the galaxy. And that precision is so good, we can actually use them as a GPS system for navigating deep space. On top of that, watching how their massive gravity warps the space-time around them gives scientists a way to rigorously test Albert Einstein's theory of general relativity in environments we could literally never recreate on Earth. They are the key to understanding how matter and fundamental physics behave under the most extreme conditions imaginable. And yet, even with everything we've learned, there's still this profound mystery at the center of it all. The pressure right at the core of a neutron star is so unimaginably high that even the neutrons themselves might get crushed out of existence. So what truly lies at that core? Are we talking about a soup of freely roaming quarks, some kind of exotic particles called hyperons, or maybe an entirely new, stable form of material known as strange matter? The answers to those questions are still out there, hiding in the dark, spinning hearts of these stellar remnants, just waiting to trigger the next massive breakthrough in fundamental physics. Thanks for learning with us today, and as always, keep questioning the universe.